Welcome, curious minds, to another deep dive. Today, we're plunging into a question that, while at first glance it feels simple, yet it quickly reveals these astonishing layers of complexity. How do we, whether as individuals navigating our own hopes or as parts of these vast, intricate systems, how do we maintain focus? Maintain that genuine drive towards a goal when the path ahead is long, winding, constantly shifting beneath our feet? It's not just about setting a destination, is it?
No, not at all.
It's about that remarkable, often invisible process of staying aligned with it over extended, even, indefinite period.
That alignment piece is key.
We're talking about the fundamental glue, really, that allows for true continuity, for knowledge to accumulate and actually stick, for intent to evolve adaptively without completely derailing, even when timelines stretch out for months, years, decades even.
Right. It's resilience over time.
And this isn't just scheduling a meeting for 3 p.m. It's about ensuring the purpose of that meeting, its outcomes, its contribution to the bigger picture, remain coherent, relevant, and impactful over a truly long haul. It's the strategic thread.
It's about that underlying thread that holds these complex endeavors together through constant change. And that brings us directly, actually, to the core concept for today's deep dive, meta-temporal coordination.
MTC, yeah.
It might sound like a bit of a mouthful, I know, but trust me, it's a profoundly sophisticated and incredibly insightful way to understand precisely how continuity, how evolving knowledge, and how shared intent are managed across these extended periods and iterative processes in truly complex systems.
Exactly. Think big.
Think about, say, a giant global organization launching a new, revolutionary product line that takes a decade to develop. Or even something as intricate and personal as your own brain, keeping you focused on a lifelong dream, adapting to countless unforeseen obstacles along the way.
That brain example is powerful.
And for this deep dive, we've pulled together some truly fascinating research material that, honestly, astonishingly bridges cutting-edge organizational theory, deep neuroscience, and even the forefront of AI development.
It really does connect surprising fields. It offers some genuinely surprising and powerful connections that I'm really eager to explore with you.
Indeed. And our mission, really, in this deep dive is to unpack what metatemporal coordination truly means. We want to explore how our own brains, and specifically through the lens of a molecule we often simplify, dopamine, how our brains exemplify this remarkable ongoing process in a profoundly intrinsic way.
The pleasure chemical doing strategy.
Kind of, but so much more. And we'll also dig into how the brain's fundamental internal timing mechanisms provide the bedrock, the very underlying framework for such sustained, adaptive, goal-directed behavior. It's about uncovering the deep principles of long-term success, both in us and in the systems we build. Okay, let's unpack this fascinating idea and see what our incredible sources reveal.
That's a perfect framing, a fascinating idea indeed, and one that resonates on so many levels. Let's start then by getting a clearer handle on what we mean by metatemporal coordination, MTC, because as you hinted, it truly is so much more than just simple timing.
Absolutely. So at its core, metatemporal coordination is about the intelligent management and continuity of shared context, knowledge, and intent. And that's across extended time frames and iterative processes.
Intelligent management, okay.
Right. The sources emphasize its critical relevance in any complex system. Think about multi-agent collaborations, different teams, maybe different individuals, working together towards a common, evolving aim.
Like a big research project.
Exactly.
Yeah.
Or consider large organizational efforts like developing a new vaccine or building a complex piece of infrastructure, which unfold over many years and through countless phases. MTC is what ensures everyone and everything is moving in the same adaptable direction, even when the goalposts seem to subtly shift or the environment fundamentally changes.
So it's not just aligning a schedule.
No, absolutely not. It's aligning the purpose, the understanding, and the collective will through an unfolding narrative of time. It's the story, not just the timestamps.
That's a brilliant distinction. It's about the entire narrative then, not just individual sentences. And to really grasp MTC, it seems crucial to understand how it fundamentally differs from what we typically call standard temporal coordination. We all do that every day, don't we?
We do, constantly.
Yeah.
Standard temporal coordination is, like you said, about simply timing actions. It's ensuring specific, discrete events happen at precise moments.
Be there at 3 p.m.
Exactly. Be there at 3 p.m. for the meeting, or launch the rocket at precisely T-minus 0 seconds. It's about synchronizing isolated events, making sure they occur in the right sequence at the right clock time. It's essential, of course, but it's finite. relatively static.
Right, it's about hitting specific marks.
But MTC is fundamentally different, far more sophisticated. It's about ensuring that the underlying goals, the evolving knowledge base, the dynamic roles of participants, and the overarching strategies involved all persist and evolve cohesively.
Cohesively, okay.
And that's over long periods and across multiple, often sequential or overlapping phases of an endeavor. It's about maintaining the why, the ultimate purpose, and the how, the evolving method, through ongoing change, unforeseen challenges, and integrating new information.
Purpose through time, not just at a point in time. That's a great way to put it.
Precise.
So it's the difference between, say, a single performance and a multi-year rehearsal leading to a series of evolving performances.
That's a good analogy.
To make this truly tangible for you, let's maybe revisit that analogy of a multi-year space mission to Mars. Standard temporal coordination is certainly crucial there, right?
Absolutely critical.
It's scheduling the rocket launch down to the second, coordinating the precise timing of engine burns, syncing data transmission windows between Earth and the spacecraft. Those are vital, singular points in time, highly synchronized.
Checkpoints, essentially.
But meta-temporal coordination, MTC, that's what ensures that the scientific objectives set a decade ago still make sense and are still vigorously pursued, even after new discoveries about Mars change our fundamental understanding of the planet's geology or atmosphere.
So it adapts the why.
Exactly. It's about making sure the team's evolving understanding of planetary conditions, gathered from previous missions or initial surveys, is integrated seamlessly into the design of the next rover or the plans for a human landing site.
Integrating new knowledge constantly.
It's about adapting the roles of mission control specialists as new challenges arise. Maybe a dust storm threatens a landing or a crucial piece of equipment fails, and ensuring that the long-term strategic plans for colonization or exploration remain coherent, adaptable, and aligned.
Even with personnel changes.
Right. Despite unforeseen technical glitches, new scientific data pouring in, or even significant changes in personnel over the span of a decade or more. It's the grand overarching symphony where every individual note and movement contribute to an ever-evolving masterpiece. It's truly about managing continuity amidst constant flux.
It's a powerful distinction.
Yeah.
And this leads us directly to why MTC matters so profoundly, both in complex organizations and, as we'll definitely get into, within our own minds. It is absolutely crucial for sustained, goal-directed behavior and for ensuring true adaptability in the face of deep complexity and the relentless march of time.
Without it, things just fall apart.
Essentially, yes.
Yeah.
Think about it. Without this meta-temporal management, any complex system, be it a multinational corporation striving for market leadership, a massive scientific research program like the Human Genome Project, or even our own cognitive processes navigating a long-term personal ambition, would inevitably drift.
Lose focus.
Exactly. It would lose its original context, shed vital accumulated knowledge as individuals or teams rotate, and ultimately fail to achieve its long-term objectives. It's what prevents a coherent effort from degenerating into a series of disconnected short-term actions.
Just reacting instead of progressing.
Precisely. It's the invisible hand guiding long-term purpose in a relentlessly dynamic world, ensuring that today's actions aren't just efficient, but relevant to tomorrow's evolving vision. Without it, you're just reacting, not truly progressing towards something meaningful.
Understood. So MTC is the sophisticated conductor of our long-term efforts. Now, here's where it gets really fascinating and perhaps a little surprising. As you said earlier, our own brains, through a molecule we often simplify, dopamine, are performing this very trick, this meta-temporal coordination all the time.
They are indeed. It's an intrinsic part of how we function.
It's not just a theory about organizations, it's happening in our heads.
It's quite true, and it's one of the most compelling insights from our sources. The research suggests a profound connection. Dopamine signaling in the brain can be seen as an intrinsic biological example of meta-temporal coordination.
Wow. Okay.
It's not just about that sudden rush you get from a reward, like winning a game or eating something delicious. That's part of it, but not the whole story. Instead, dopamine manages how motivation and reward contexts are maintained and adapted across a vast array of timescales within the brain.
Across different timescales.
Yes. This includes dynamically integrating past experiences, calibrating our responses to immediate stimuli, and even fine-tuning our future expectations. All of this enables truly adaptive decision-making and effective learning over the long haul.
So it's continuous, multi-layered.
Exactly. Not a simple one-off reward hit. It's a dynamic system for valuing and pursuing goals across time.
That's incredible. So dopamine isn't merely a simple reward chemical telling us good job. It's a strategic manager across time, a vital component of our internal MTC. Our sources really highlight this by breaking down dopamine's role into what's called its dual nature, supporting both continuity of motivation and context. Can you elaborate on that?
Certainly. This duality is fundamental. First, we have what's known as tonic dopamine.
Tonic, like a baseline.
Exactly like a baseline. Think of this as the steady, persistent background hum of dopamine activity in certain brain regions. It's not about sudden spikes, but rather a persistent baseline level. And this helps maintain an overall state of engagement, readiness, and a general sense of this is worth pursuing. This sustained presence of tonic dopamine is absolutely crucial for maintaining a foundational level of interest and drive over long periods.
So that's what keeps you going on a long project.
It's a big part of it, yeah. It's what keeps you returning day after day, week after week, even when there are no immediate big flashy rewards. It provides the sustained motivational context, a kind of internal North Star guiding your general orientation.
Okay, that's tonic. Then contracting that, we have phasic dopamine.
Right. Phasic. These are the short, rapid bursts of signaling that occur in direct response to salient or rewarding events, or even cues predicting them.
That spikes.
Exactly. These are the sharp, spike-like releases that highlight immediate importance, the aha moment when you suddenly solve a complex problem, the small win in a larger project, the taste of something delicious, or the satisfying completion of a small task. They act as immediate high-fidelity feedback signals, marking moments of significance and providing precise learning signals.
Okay, so if we connect this back to MTC, this duality, tonic, and phasic dopamine, it perfectly mirrors the meta-temporal need to maintain a consistent background context, that long-term strategic awareness, the overall mission, supported by tonic dopamine.
The steady hum.
While simultaneously dynamically responding to new stimuli or changes in the immediate environment, which is handled by those sharp phasic bursts.
Spot on.
It allows us to keep the grand long-term game in mind, that ultimate objective, while still being agile enough to seize immediate opportunities, learn from small successes, or pivot rapidly when unexpected challenges arise. It's a beautiful, elegant biological system for managing both the forest and the trees, isn't it?
It really is, ensuring that our short-term actions are always contributing to the long-term vision.
And this dynamic integration allows the brain to perform quite an impressive juggling act, you were saying.
Absolutely. It can manage demanding long-term goals, like dedicating years to becoming proficient in a complex skill, say a surgeon or a concert pianist, or meticulously saving for retirement over decades. That takes sustained tonic drive.
Right, the long haul.
But at the same time, it can successfully integrate and respond to immediate gratifications, enjoying a delicious meal with friends, taking a brief moment of leisure, achieving a small daily milestone. Those phasic hits matter too.
So it balances both.
Yes, both short-term enjoyment and long-term discipline are integrated into a cohesive, purposeful stream of behavior. It ensures that our immediate actions contribute to, rather than detract from, our long-term aspirations. It's the brain's incredibly sophisticated way of saying, yeah, enjoy that cupcake, but don't forget you're also training for a marathon, and maybe that cupcake is part of the reward system keeping you going.
That's a fantastic image. And this dynamic adaptation extends directly to how dopamine influences learning itself. It's not just about enjoying the reward, it's about using that signal to profoundly refine our approach to future actions.
Absolutely. Dopamine plays a profound modulatory role in neuronal activity and plasticity.
Plasticity, the brain rewiring itself.
Exactly. The brain's incredible fundamental ability to strengthen or weaken connections between neurons based on experience. It's how we learn and adapt at a cellular level. And dopamine isn't just a passive reward signal, it's an active instructing force for learning. It helps the brain adjust learning, behavior, and expectations as new reward information is integrated over time.
How does that work?
Well, if an action leads to a better outcome than predicted, that surge of phasic dopamine reinforces the neural pathways associated with that action, making it more likely to be repeated.
Strengthens the connection.
Right. And if the outcome is worse than predicted, dopamine signaling adjusts in a way that signals for an adjustment or correction in behavior. It flags that something didn't work as expected.
So it's a continuous biological feedback loop.
Precisely. Constantly informing us what works and what doesn't, allowing for perpetual refinement.
So, drawing a direct parallel to MTC again, this mechanism truly links to MTC's concept of flexible role and task allocation across evolving goals and feedback.
It does. very strongly.
Just as a complex project team adapts its approach based on evolving information from the field, shifting resources, reassigning tasks, tweaking strategies based on performance metrics, our brain uses dopamine to constantly adapt its own internal strategies for approaching tasks.
It's optimizing on the fly.
It's continually refining its roles for various tasks, learning more efficient ways to achieve desired outcomes based on the precise feedback it receives through these signals. It's like having an internal project manager constantly optimizing your performance, making real-time adjustments for long-term gains.
That's a great way to think about it. And think about learning a new skill that demands sustained effort, like playing a musical instrument. Let's say the violin, just as an example.
Okay, the violin, tough one.
Very. When you first pick it up, your movements might be clumsy, the sounds, maybe not so harmonious.
Definitely not.
But each time you draw the bow or place your fingers on the strings, your brain is receiving immediate feedback, auditory, tactile, even visual. If it sounds good, or even just better than before, a phasic dopamine burst fine-tunes the underlying motor sequences, reinforcing those precise movements.
Ah, okay. Rewarding the good attempts.
And if it sounds off, that signals a prediction error. We'll get more into that prompts an adjustment. This constant fine-tuning, driven by dopamine-mediated learning, allows for incredible dynamic adaptation of your movements, your neural pathways, and your expectations over days, weeks, even years of practice, leading to mastery.
That's truly meta-temporal coordination at work within your own motor learning system.
Exactly, ensuring continuous improvement towards a distant goal.
And a huge part of that continuous refinement, that iterative improvement you mentioned, comes from something specifically called reward prediction errors, which the source material highlights as crucial feedback and learning loops. This sounds absolutely critical for MTC.
It is perhaps one of dopamine's most critical functions in this meta-temporal context. Dopamine's role in encoding reward prediction errors, RPEs, is precisely what it sounds like. It's the neural signal representing the difference between what was expected to happen and what actually occurred.
Expected versus actual.
Okay. And crucially, this isn't just about the presence or absence of a reward, but also its timing and its magnitude.
Ah, timing and size matter too.
Very much so. For instance, if you expect a small reward but get a large one, that's a positive RPE signal strengthening the preceding action. If you expect a reward quickly and it's significantly delayed, that's a negative RPE, signaling that your timing prediction was off, prompting adjustment.
Got it. So it's quite nuanced feedback.
Extremely. And these RPEs are essential because they facilitate continuous feedback to refine behavior and expectations over both short and long timescales. This is how we truly learn from successes, from mistakes, and critically, from delayed outcomes.
Delayed outcomes are key for long-term goals, right?
Absolutely. If you're working on a multi-year goal, like writing a comprehensive history book, the small RPEs you get from finishing a chapter ahead of schedule or receiving unexpectedly positive feedback on an early draft are crucial. They reinforce your efforts, signal you're on the right track, and help refine your writing process, even if the ultimate reward of publication is years away. It's how the brain keeps scoring the game, even when the final whistle is far off.
That makes perfect sense. This mechanism shows a strong alignment with MTC's fundamental focus on robust feedback mechanisms that update future steps based on retrospective data.
Yes, the parallels are striking.
Our brain is essentially running a sophisticated internal post-mortem analysis on its own actions, constantly asking, what did I predict? What actually happened? How can I adjust for next time? Whether that's the next millisecond, the next hour, or the next month.
It's an incredibly efficient self-correcting system.
Allowing for continuous improvement towards a goal that might shift or deepen over time.
And this continuous feedback loop is precisely why humans are such powerful learners and adapters. It allows for the gradual shaping of incredibly complex behaviors, from mastering a profession to building a long-term relationship over extended periods.
It's not about immediate perfection.
No, not at all. It's about continuous, data-driven improvement driven by a precise biological mechanism. It ensures that our behavior is always optimally aligned with the current understanding of the environment and our goals.
And it's not just about one specific timescale, is it? Dopamine seems to orchestrate behavior across multiple, vastly different timescales, which is truly remarkable for a single neurochemical system.
That's right. The source highlights that dopamine signaling supports behavioral adaptation across immediate, midterm, and longer-term timescales.
Can you give examples?
Sure. Think about the immediate. reacting to a sudden, unexpected sound, or quickly avoiding an obstacle in your path. That's rapid response.
Okay.
Then there's the midterm. Learning a new complex habit over a few weeks, like consistently waking up early for exercise or mastering a new software program, requires persistence over days or weeks.
Got it. Habits.
And finally, the longer term. Maintaining a motivational drive for years to achieve a major career goal, like becoming a tenured professor or launching a successful startup, or a personal aspiration like getting a demanding degree or building a business from scratch, that's years, even decades.
And dopamine helps manage all three.
Yes. Through its varied signaling patterns, tonic maintaining the background, phasic marking progress and errors, it helps bridge these different temporal gaps, ensuring coherence across scales.
And this directly connects to MTC's capacity for orchestrating and managing short, medium, and long-range planning and actions in highly coordinated systems, like organizations or AI.
Exactly. Our internal motivation system, largely fueled by dopamine, is essentially a master planner across time. It ensures that the immediate choice to, say, practice an instrument for an hour.
The violin again?
Yes. That practice is connected to the midterm goal of improving your skills for a recital next month, which in turn feeds into the long-term aspiration of becoming a proficient musician. It's all interconnected, thanks to this multi-scale orchestration by dopamine.
It prevents the short-term impulses from wrecking the long-term plans.
Precisely. This integrated control across different temporal scales is absolutely vital for sustained goal pursuit. It ensures that those short-term actions contribute meaningfully to long-term objectives. Without this multi-scale orchestration, we'd be adrift, constantly responding to the nearest stimulus without any sustained direction or purpose. We wouldn't be able to defer gratification or work towards distant rewards effectively.
Okay, so let's try and pull this dopamine thread together.
Right. So to synthesize all of this, dopamine's role is incredibly integrative. It acts as a central player in our brain's meta-temporal coordination. It dynamically manages how motivation and reward contexts are maintained and adapted across varying timescales, serving to integrate past experiences, immediate stimuli, and future expectations for truly adaptive decision-making and highly effective learning.
The brain's dynamic curator of time. I like that.
It fits, doesn't it? Ensuring that every piece of information, regardless of when it was learned or when it's expected, contributes coherently to our overall goal-directed behavior.
And the really profound implication here, which our sources explicitly highlight, is that this very metatemporal coordination framework, derived from observing complex human-made systems like organizations, is actively used in large-scale AI and organizational projects today.
It is. That's a key point. These projects employ similar principles, maintaining context, adapting roles, integrating feedback across timescales to ensure continuity, adaptability, and alignment across complex, multi-agent, and multi-phase initiatives.
So it's a mirror image, almost.
It mirrors precisely how dopaminergic systems in our brains maintain goal-directed behavior through integrated multi-timescale signaling.
That's fascinating. So it's not just an abstract theory, it's a design principle in the real world. Can you give us some concrete examples of how this MTC framework is applied in AI or organizational settings?
Certainly. Consider agile software development. You probably know this. It's widely adopted in tech.
Right, agile sprints.
Exactly. Here, the long-term vision for a product that's the tonic goal, the background hum, is broken down into short iterative sprints. Those are the phasic actions. Each sprint delivers a small functional piece of the product, and critically, the team continuously gathers user feedback. This feedback acts like the reward prediction error.
The RPE connection.
Right. If a feature is more useful than expected, it's reinforced, maybe expanded. If it causes issues or users don't like it, that signals a need for immediate adaptation in the next sprint.
Constant correction.
This dynamic, multi-time scale feedback loop allows the product to evolve and stay aligned with user needs over years, even as the market shifts. That's pure MTC in practice.
Makes sense. Another example.
Okay, think about complex scientific research consortia, like those tackling climate change or a global pandemic response.
Huge, multi-year efforts.
Massive. You have hundreds of research groups across the globe, each working on specific sub-problems. Those are the phasic efforts, but all contributing to an overarching long-term scientific objective, the tonic goal. MTC here involves things like shared data platforms to ensure continuity of knowledge, regular intergroup communication to maintain shared context, and flexible funding models that adapt as new breakthroughs or challenges emerge.
Keeping everyone rowing in the same adaptable direction.
Exactly. It's about maintaining coherent scientific progress over decades. far beyond the lifespan of any single grant or individual researcher.
Okay, one more, maybe AI.
Sure. How about self-driving car systems development? The ultimate goal is fully autonomous, safe driving. That's the long-term objective, the big vision.
The holy grail.
Right. But the system is constantly fed data from millions of miles driven, encountering new scenarios, unexpected events, and it receives prediction errors when its algorithms make mistakes or encounter situations it hasn't seen before or handled poorly.
Learning from mistakes.
Crucially, yes, these errors aren't just noted. They are fed back into the learning models, causing the AI to adapt and refine its behavior over vast timescales, constantly improving its ability to handle unforeseen, real-world complexities. This continuous learning and adaptation, driven by feedback loops across different temporal scales.
That's MTC in the machine.
It's a prime example of MTC in artificial systems. And this raises a really important question. What more can we learn about designing adaptive systems, whether they are technological or organizational, by digging deeper into the intricate workings of our own brains?
It's a powerful validation of the brain's incredible efficiency and adaptability.
Absolutely.
That's a truly profound point. It really moves MTC from an abstract concept to a practical blueprint. So, okay, if dopamine is a key engine of meta-temporal coordination in our brains, what's the underlying machinery? What's the very clockwork that allows for all this precise management of time in the first place? We're now talking about the fundamental neurobiological timing mechanisms, right?
Yeah, exactly. You've got it. Meta-temporal coordination is indeed a high-level functional framework, but it doesn't exist in a vacuum. It needs hardware to run on, so to speak. It parallels and profoundly leverages the brain's intricate neurobiological timing mechanisms, or NBTM. These are the sophisticated systems that govern our perception and control of time itself.
How we sense and use time?
Right. It's about how the brain creates and utilizes time as a fundamental building block, a sort of neural scaffolding for sustained and complex behavior. You cannot possibly manage context and goals across scales if you don't have robust and flexible mechanisms for sensing, tracking, and producing time in the first place.
So the timing mechanisms are foundational.
They are the foundational substrate upon which MTC is built. No timing, no MTC.
And what's particularly fascinating, according to our sources, is that the brain doesn't seem to have one single centralized master clock that dictates all timing. Instead, it relies on a far more flexible and distributed system. This seems critical for the adaptive nature of MTC we've been talking about.
That's absolutely right. Neurobiological timing isn't mediated by a single monolithic clock ticking away somewhere in our skull. That would be too rigid, too vulnerable.
Right.
Instead, it's a wonderfully flexible and robust system, mediated by multiple overlapping brain systems that can engage and disengage dynamically depending on what the specific task demands and what the environmental context requires.
Different clocks for different jobs?
Sort of, yeah. This distributed and adaptable nature means the brain can be incredibly efficient and versatile at managing different kinds of timing, from rapid millisecond precise responses to prolonged hours-long engagements, often simultaneously. It's like having a suite of specialized timers, each perfectly suited for different temporal demands.
And this inherent adaptability in how the brain handles time directly mirrors MTC's core principle of dynamically adapting shared goals and processes over varying timescales.
The parallel is very strong.
Just as a complex organization might shift its focus or restructure its teams depending on evolving project needs, the brain itself shifts its internal clocks, or emphasizes different timing networks as needed for the specific job at hand.
It reconfigures itself based on the task.
It's a testament to the brain's profound flexibility and efficiency, allowing it to maintain coherence even when faced with novel or unpredictable temporal demands.
And this distributed nature allows for incredible versatility and robustness in our temporal processing. Think about it. Our brains can effortlessly judge the subtle rhythm of music.
Yeah.
Predict the precise moment to intercept a moving object like a thrown ball, or anticipate complex sequences of events in a rapid-fire social interaction. All these different temporal demands, often occurring simultaneously, are handled by this flexible, overlapping network, rather than relying on a single point of failure. It's truly impressive engineering.
Okay, so it's distributed, but are there key players, core regions involved?
Yes. While it's distributed, there are key regions that form a sort of core timing network, crucial for executive control and integrating these temporal processes. Our sources highlight several critical areas. First, the supplementary motor area, SMA. This is crucial for planning and coordinating complex movements, including their precise timing, especially for actions you initiate yourself.
Motor timing, okay.
Then the basal ganglia. These are essential for sequencing actions, forming habits, and ensuring the precise timing of both physical actions and even abstract thoughts, like stringing words together smoothly in a sentence.
Sequencing and habits. Makes sense.
The prefrontal cortex, often called the seat of executive control, is deeply involved. Think working memory, planning, sustained attention, and the temporal organization of our behavior. It's where we make those long-term plans and keep them in mind.
The executive function hub.
Right. And finally, the cerebellum, back of the brain, which is renowned for fine-tuning movements, coordination, and especially for sub-second timing, like detecting subtle temporal gaps or rhythms in sound or movement. Very precise.
Wow. What's fascinating here is how these distinct areas, often associated with different functions, motor control, higher cognition, coordination, they all converge and cooperate to create our incredibly sophisticated sense and use of time.
It's a real network effect.
So how do these systems working together provide the underlying support for something as high level as MTC?
Precisely. These regions work in concert to organize and coordinate timing signals across motor, perceptual, and cognitive domains. They don't just time things in isolation, they weave together the temporal fabric of our entire experience. And in the context of our discussion, these systems can clearly be viewed as the neural substrates supporting meta-temporal coordination. They provide the fundamental, ongoing temporal context,
For background timing.
while simultaneously adapting to new inputs or evolving goals, offering the crucial underlying temporal scaffold upon which all that complex long-term behavior is built. It's the physical infrastructure that enables the intelligent management of goals and knowledge over extended periods.
So without these precise and adaptable internal clocks, MTC in the brain just couldn't function.
It simply couldn't. It needs that temporal foundation.
So it's not just about timing discrete actions, but the entire continuous flow of behavior and cognition. And speaks of flow, the brain's timing also operates at multiple hierarchical scales, which again sounds very much like MTC's capabilities in managing short, mid, and long-term endeavors.
Absolutely. Timing in the brain operates at a fascinating hierarchy of multiple scales. It's not just one speed.
Like what scales are we talking?
We're talking everything from milliseconds, the incredibly precise timing needed for the rapid production of speech sounds, or the exact moment you swing a golf club to hit a ball with perfect contact, super fast.
Micro timing.
Then there are seconds or minutes of timing involved in more complex cognitive tasks, like anticipating the next sentence in a conversation, remembering the precise duration of a complex event you just witnessed, or knowing roughly how long you've been working on a particular task.
Everyday durations.
Right. And finally, longer timescales, extending to hours, days, or even weeks, for instance, the timing of our sleep-wake cycles, circadian rhythms, or the anticipation of recurring events in our lives, like weekly meetings or seasonal changes.
So the brain handles all these diverse temporal demands, often in parallel.
Seamlessly.
And this directly links to MTC's capacity to manage short, mid, and long-term planning and adaptation in large-scale systems. Our brain integrates these immediate neural timing signals, those millisecond precise movements, with sustained motivational and behavioral state that might span days, weeks, or years.
It connects the micro to the macro.
It's like a master conductor orchestrating a complex symphony, ensuring every single note is played precisely, but also that each movement contributes coherently to the overall arc of the entire piece, which unfolds over hours. It ensures micro-level precision serves macro-level purpose.
That's a beautiful analogy. And this multi-scale temporal processing is truly fundamental to our ability to function coherently in a dynamic world. It allows us to address immediate demands while simultaneously keeping our long-term aspirations firmly in view.
Keeps the big picture in focus.
Exactly. It's what prevents those immediate impulses from completely derailing our grander plans and ensures that our short-term actions are always contributing to our long-term objectives. It's not just about timing the now, but timing the now in relation to the then and the future, building a cohesive temporal understanding.
What's truly intriguing then is that this internal clockwork isn't perfectly rigid, is it? Our sources talk about temporal variability, which seems counterintuitive for something that's supposed to be precise. You'd think a clock needs to be perfectly consistent.
It is, and it's a critical, often misunderstood point. Neural timing isn't a rigid, perfectly consistent stopwatch. If it were, we'd be much less flexible. It exhibits what's called temporal variability, specifically through what scientists sometimes describe as stochastic transitions across neural states. Essentially, there's an inherent noise or slight useful randomness in the precise timing of neural events.
Useful randomness.
Well, here's the key. This isn't a flaw. It's a fundamental feature that actually enhances our adaptability.
Okay, explain that.
This intrinsic variability is incredibly important because it paradoxically allows for flexible action timing and enhanced adaptability to environmental changes. If our actions were always locked into precise, unchanging rhythms, we'd be far less adaptable. Think about it.
Right.
Imagine trying to catch a ball if your brain could only anticipate its arrival at one exact pre-programmed millisecond. You'd miss it almost every time the throw was slightly different.
Because the real world isn't perfectly predictable.
Exactly. This inherent variability, this slight wiggle room in our neural timing, allows for subtle adjustments, a recalibration that lets you react dynamically to the unexpected, to a slightly off-course throw, a sudden change in rhythm, or shifts in the environment.
So this intrinsic variability actually supports meta-temporal flexibility rather than hindering it.
Precisely. It enables our internal systems and, by extension, us to constantly update plans and goals based on ongoing feedback and changes over time, rather than being stuck on a predetermined rigid course.
It's the give in the system.
That's a good way to put it. It emphasizes the dynamic, nonlinear nature of brain processes and how this very imperfection or noise actually enhances our capacity for long-term adaptation and resilience. It's the built-in flexibility that allows for true learning, innovation, and evolution in our behavior.
Without it, we'd be too brittle.
Exactly. Too brittle to adapt to a constantly changing and unpredictable world. It's a core component of its robustness and its capacity for truly adaptive MTC. It provides the necessary degrees of freedom for real-world interaction.
Okay. And bring it full circle now. These sophisticated neurobiological timing mechanisms aren't operating in isolation, are they? Our sources are very clear that they interface directly with our reward and motivation systems, specifically the dopamine system we just explored. This seems to be the ultimate integration point.
This is indeed the crucial point that ties everything together, like the final piece of a complex puzzle. The brain's neurobiological timing mechanisms interface directly and inextricably with reward-related processes, like dopamine signaling.
They talk to each other constantly.
They have to. This integration isn't just a coincidence. It's fundamental to how our brains learn and adapt across time. How we learn, how we stay motivated, and how we correct our errors are all deeply dependent not just on what happens, but crucially, on when it happens, the precise timing.
Timing is everything, as they say.
In this context, very much so. This integration means that the timing of a reward, or the timing of a mistake, provides incredibly critical information. It reinforces learning, motivation, and prediction errors across various timescales.
How so?
Well, for example, if you perform an action and a reward appears sooner than expected, that precise timing information, processed through dopamine, provides an even more powerful signal that reinforces the preceding behavior. Wow, that worked faster than I thought.
Okay, faster reward, stronger learning signal.
Generally, yes. Conversely, if a predicted reward is significantly delayed, that timing error also provides critical information for future adjustments. It might prompt you to seek alternative strategies or reconsider your expectations about how long something should take. That took way too long. Maybe there's a better way.
So this integration is absolutely critical for metatemporal coordination.
Foundational.
Our sustained behavioral goals inherently depend on a motivational context, that tonic dopamine background, and a robust learning history built on those reward prediction errors, critically incorporating their timing.
Yes, the history matters.
This allows us to sustain and modify our behavior over extended periods, adapting dynamically to the flow of information over time. If we connect this to the bigger picture, it means that our ability to plan and adapt over the long haul, to stay focused on that distant Mars mission or that lifelong career goal, is intimately tied to how our brain rewards us and how it learns about time, duration, and precise timing. It's a holistic, exquisitely tuned system.
That's the perfect summation. Metatemporal coordination is truly a high-level functional framework that parallels and profoundly leverages the brain's intricate neurobiological timing mechanisms to manage complex adaptive behavior over extended time frames.
It emerges from the interaction.
Exactly.
Yeah.
It's not a completely separate process, but rather an emergent, sophisticated property of these fundamental timing systems interacting with our motivational architecture. In essence, neurobiological timing systems offer the crucial neural foundation. This includes those flexible distributed timing networks we discussed, and also the intrinsic temporal dynamics, like that valuable variability. Together, these enable metatemporal coordination's core functions: the intelligent maintenance of continuity, remarkable adaptability, and persistent goal alignment across all those crucial multiple timescales.
It's the brain's internal architecture for making sure you stay on track, continue to learn, and adapt.
No matter how long or winding the journey, that's the essence of it.
And what a journey it's been today. We've taken a truly fascinating deep dive into meta-temporal coordination and brain timing. We start by understanding that meta-temporal coordination is far more than simple timing. It's the intelligent management of shared context, knowledge, and intent over long, evolving periods, absolutely crucial for any complex, sustained endeavor, be it an organizational project or a personal aspiration.
Right, that core definition.
Yeah.
And we then explored how our own brains employ this sophisticated process in an intrinsic biological way, primarily through the dual nuanced interplay of tonic and phasic dopamine.
That amazing dopamine system.
This remarkable molecule manages our motivation and learning across various timescales, integrating past experiences, immediate stimuli, and future expectations to keep us aligned and profoundly adaptive.
All of this, as we've learned, is underpinned by a flexible, distributed network of brain regions dedicated to timing.
The NBTM.
These neurobiological mechanisms create the very temporal scaffold upon which our sustained behaviors are built, constantly adapting and learning from experience, even leveraging their own inherent variability to enhance flexibility and resilience.
The foundation and the flexibility.
So here's the aha moment we want to reinforce, a powerful takeaway from our sources. Your brain isn't just reacting to the immediate present. It is, by its very design, a master of long-term strategy. An incredibly sophisticated system constantly performing this complex meta-temporal coordination. It's doing this right now to keep you aligned with your goals, to learn from every past experience, and to adapt seamlessly to whatever the future throws your way, ensuring your efforts remain coherent and purposeful.
It's constantly working behind the scenes.
And as you go about your day, pursuing your own projects, trying to build new habits, or striving towards truly long-term aspirations, consider this. If your brain is constantly performing this intricate metatemporal coordination to keep you focused and adaptive, how might understanding this very process, this delicate dynamic dance between long-term intent, immediate feedback, and flexible timing, allow you to better manage your own time, enhance your motivation, and sharpen your strategic efforts to achieve what truly matters to you?
Using the brain's blueprint.
Exactly. It's a profound blueprint for effectiveness, hidden right inside your own head, waiting for you to perhaps consciously harness its power. Thank you for joining us on this deep dive. We hope it's given you some fresh perspective on the incredible machinery within you.